To start out, I just want to give a little bit of background. Here I've got kind of a simplified architecture diagram of some of the P2P code. At the base, you can see there's sort of a layered structure. At the base, we have the P2P network. It's responsible for finding peers on the network. That's the discovery part of the protocol. Establishing connections to those peers and negotiating capabilities. And capabilities are just version subprotocols, so peers can run any number of subprotocols. The main one we deal with is ETH, but there's like the light client protocol, Whisper, Swarm, all that stuff. All that is handled at the P2P network layer. On top of that, we've got the ETH protocol manager. So this is specific to the ETH subprotocol. And basically what this does is it handles all the default behaviors of the ETH subprotocol. So for example, when you're running this protocol, the first message you send to your peer has to be a status message. So this manager enforces that. Peers can request data from your node. So the manager serves that data to the peers. It's basically just handling all the default things that you have to do to be a good peer within the context of the ETH subprotocol. It also exposes some utilities for sending queries over the ETH protocol. And these utilities are used by the synchronizer, which sits at the top of the diagram here. Synchronizer is basically in charge of keeping the local client in sync with network, as the name suggests. There are two broad classes of behavior that the sync is in charge of. So it's got a block propagation manager that's in charge of listening for new blocks as they propagate across the network. So it's looking at activity at the chain head and watching as the chain advances. And then there's the downloader that's responsible for pulling historical data. So if you spin up your client and you're at block 0 and the network's at block 7 million, the downloader is in charge of getting you up to 7 million. In terms of full and fast sync, we're mostly focusing on the downloader. And I'm just going to give an overview of full sync first, and then we can kind of compare and contrast with fast sync. So the first thing to recognize when you're thinking about the environment that the synchronizer is working in, we talk about blockchains, but really in terms of what the synchronizer sees, there's kind of a block tree. So that means that you've got canonical blocks out there, but you also have forks and non-canonical blocks, and you have to deal with all that chaos. So the first step that the synchronizer takes is to wait for peers, because you can't do anything without peers. And what do we know about these peers? When they connect, they'll send us a status message. So that tells us what network they're running on. And it also gives us information about their chain head, their best block hash, and total difficulty. And then as blocks propagate across the network, we can watch for those messages to see if peers are advancing, so we can kind of estimate where their chain is. And given that information, we're going to select our best peer, which is the peer with the heaviest chain head block. And so in this little diagram, that's going to be the peer in the top center there. And so once we've selected a best peer, that basically collapses this tree into a single chain. So it kind of simplifies the view of the network. And then the next step is to find our common ancestor. So in the simple case, the common ancestor with this peer is just going to be the genesis block. If you already had some local block data, you'd basically have to search through those local blocks and find the highest block that your peer knows about, and that would be the lower bound. You obviously don't want to be downloading data that you already have, so it's just a lower bound on the sequence of blocks that you're downloading. Next step, we ask for the sequence of checkpoint headers. So these are evenly spaced headers along the chain. And basically what that lets us do is it defines small segments of this chain, and then we can farm out requests for the data associated with those chain segments across our peers. So because we have these checkpoints from a single chain and we have those hashes, we know that the requests we send out are going to be matching this singular chain that we want to download. And as far as what those requests look like, we're going to pull headers. As those headers come in, we'll fully validate each of them. We're going to request bodies. Those bodies have OMERs and they have transactions. So we'll validate the OMERs, we'll execute the transactions. And as we execute transactions, we're generating state data. And after executing the full set of transactions in a body, we're going to get a state root, so we can validate that state root against the corresponding header. We're also producing transaction receipts, so we can match the transaction receipt root to the corresponding header as well. And now for fast sync. So starting out, same kind of picture. There's some messy network and some number of peers. The first step in fast sync is to pick a pivot block. So this is the point at which we switch from fast sync to full sync. And the basic trade-off with fast sync is that it's fast, as the name suggests, but the security is a little bit lower. So basically at some point we want to switch back to full sync and do all the full validation, and the pivot is the point at which we do that. So we'll pick a pivot block that's some distance from the chain head. Let's say it's block 7 million. And we'll ask all of our peers, hey, what block do you have at block 7 million? Those responses will come back and we kind of tally those responses to get kind of a vote on the pivot block. When we find a pivot block that has enough support, we'll select that. So in this little cartoon, I've got this little green highlighted block with 3 votes there. So we'll say that we're going to select that as our pivot block. The next step is the same as before. So we're going to select our best peer. But now there's this extra bit where we validate that our best peer agrees with our pivot block, because we want to make sure that we're downloading what we expect to download. Same thing here. So now we've got a kind of simplified chain that we're downloading. The difference is that the upper bound is this pivot block. We'll again find the common ancestor. Again, request checkpoint headers that are evenly spaced. And again, farm out requests for block data across all of our peers. So the block data that we request is a little bit different, and the processing is a little bit different in FastSync. We'll request the headers, but we don't fully validate them. We only fully validate a subset of headers. For most of them, we're skipping proof of work. That's the computationally expensive slow part, so that's where some of the speed comes from. We'll request bodies, but we're no longer processing transactions. I see there's a chat message, but I'm full screen, so I can't see. But
Nico's asking, how is the pivot block defined?
So there's basically a configuration parameter that says like how far from chain head do you want to select the pivot block, and that's how we choose that. So we look at the network, we look at the most advanced chain head, and we go some distance in the past from that. So if our best peer is at block 7 million and we're configured to select a pivot block that's 1,000 blocks back, we'll just do 7 million minus 1,000, and that's the height of our pivot block. That makes sense.
Okay, thanks, Meredith.
Yeah. Yep, so for the headers, skipping proof of work validation. For the bodies, we're skipping transaction execution. So that means we're not generating state, and we're also not generating transaction receipts. For the transaction receipts, this is an extra new type of query that we run against the network. So we just ask for the receipts associated with any given block. And that leaves the state data. So in terms of the world state, basically what we do is we download a full snapshot of the world state at the pivot block. We need the world state in order to switch back to full sync mode, because we're going to be executing transactions going forward, and we need the state to execute transactions. So we'll look at the pivot block header. It's got a state root hash there. We'll send a request to the network. Can I get the node that's associated with this hash? The root node of the world state try will come back. It has a bunch of hash references, so we can send out requests for all of those. We'll get back more node data that has more hash references, and you basically just walk down the tree in this way, requesting hashes as you encounter them. This is kind of what the world state looks like in total. So if we go back here, the state root is the root of the account state trie, which is that big blob on the left. The account state trie is basically a mapping between account address and account tuple. So an account has a nonce, a balance, a code hash, and a storage trie root. So those extra bits of information, the storage tries and the code also have to be downloaded. So you've got all these leaf account values at the bottom, and for the storage tries, you download them in the same way that you're kind of downloading the account state trie. And the code is also similar. You're just requesting hashes that correspond to code. So in summary, why is it fast? We're lightly validating headers. We're not processing transactions. And since we're not processing transactions, we have to download receipts and we have to download the world state. Limitations of fast sync. So the security guarantees are not as strong. So it's a trade-off between speed and security. There's also a criticism that when we download these state tries, we're basically downloading all of these individual nodes in that trie. And strictly speaking, we could just produce those locally. Like if we had all the leaf values, we could just build a trie and we wouldn't need to download all that. So there's a lot of network requests that maybe don't need to be happening. Another issue with fast sync is that we're just requesting these hashes at random. So there's no real way for clients to optimize serving that data because they're doing all these random lookups for hashes all over the place, and that ends up being slow. And then quickly, I'll just touch on some other sync algorithms. So Parity has an alternative sync algorithm called warp sync. Basically what they do is they package up entire snapshots of the blockchain at some particular height, and nodes will download that full snapshot, which is gigabytes in size. They also avoid sending over these node data, so they just package up the leaf data and the world state, and then the client will reconstruct the world state trie from that leaf data and verify that the root node they get, the root hash of the world state trie, matches the state root hash that they expect. Some problems with parity sync are, clients are downloading this huge blob of data. They're downloading it from a single peer, so nodes can get tricked to download a bunch of data and they can't really verify until they get to the end. So they download all this data, build a world state trie, and then get a state root hash that's wrong. Well, they just have to throw all that work away. And then another issue with warp sync is that building those big snapshots is expensive for nodes. So there are a bunch of alternative kind of hybrid fast warp sync algorithms that are in development. The idea is kind of to try and take the best of both worlds. So we like the idea of downloading world state leaf data and not downloading all these intermediate nodes if we don't have to. So that's a little bit less that we need to download. But instead of doing it all in one shot, the idea is to download kind of reasonably sized chunks. So when we get these chunks of data, depending on how we pull them, we could generate Merkle proofs that they belong to the state root that we expect. Or if we're pulling them in kind of a fuzzier way, we can read through the tries that we generate and request data that we're missing. So this makes requests more efficient because we're making fewer requests with larger payloads. And hopefully these larger payloads are designed in a way that nodes can serve them more easily than just doing all these random lookups. And then we're, again, avoiding the attack where nodes download a bunch of junk data. We're pulling this data from multiple nodes, so hopefully not everyone's trying to trick us, and we can validate as we go. And then I just included a few links to some of the sync proposals that are out there. This probably isn't comprehensive, but those are just some ones that I grabbed quickly. And that's it.